Hello and welcome to this AICHE talk. My name is Jens Metzger and I'm a PhD student at the ETH Zurich. As a member of Professor Müller's Laboratory of Energy Science and Engineering, I'm investigating different granular phenomena. Today, I would like to introduce you to our results that we acquired by combining real-time magnetic resonance imaging and numerical simulations of gas bubble splitting and coalescence in fluidized bed. At first, I would like to state on the motivation of this research. As you all know, fluidized beds can be found in a variety of industries, such as chemical industry, food processing industry, and also pharmaceutical industry. Mostly they are used because of their advantageous characteristics in particle mixing and distribution of heat, for example in fluidized bed reactors. This characteristic occurs because gas bubbles rise through the bed and constantly mix the solids. If the gas bubbles get larger, they create larger mixing of the solids. However, they also create space for preferential airflow through the bubble. And so the contact between the gas phase and the solid phase decreases the larger bubbles get. So there's a trade-off in the bubble size in order to establish good solid mixing, but also to keep up heat and mass transfer. So we want to limit the bubble size. One way of doing so could be the insertion of obstacles into the fluidized bed, for example, heat exchanging tubes. As you can see on the right side of the slide, here a tube is inserted into a granular bed and performed fluidization. We can see that the insertion of the obstacle is effectively reducing the gas bubble size, but in the meantime creates heterogeneous fluidization states. For example, there is a region above the tube in the so-called wake where the fluidization is less, so a defluidized cap. Also, bubbles will preferentially occur in the vicinity of the obstacle. So we have different fluidization zones. This can, for example, lead to heat spots in a fluidized bed reactor, which is disadvantageous. So if we really want to perform better engineering on such systems, we need to understand how gas bubbles interact with such inserts. Investigations on these fields have been performed for several decades now. The problem is that if we want to investigate the interplay of gas phase and the obstacle, we either needed to have a 2D bed, so a pseudo 2D bed, or insert probes, which both change the physics of the system because the gas also interacts with the walls, so we have wall effects, or with the probes that themselves represent obstacles for the fluidized matter. If we really want to acquire information on 3D systems, we need to have insight into that system. So we need to perform measurements that really give us a look inside of the fluidized bed reactor. So our goal here is to understand the effect of obstacles on first, bubble splitting, the bubble coalescence secondly, thirdly, the fluidization and defluidization caused by the obstacle, and fourthly, the solids mixing. By using additional constraints, we want to use a method that measures all of these quantities, but at real 3D beds, so with reduced wall effects. It measures non-invasively, so we don't want to insert probes to have the original physics of the problem. And we want to have spatially and temporally resolved measurements so that we can really see how the bubble is evolving and interacting with the obstacle. In order to do so, we have decided to pick two methods. One method is the magnetic resonance imaging. This is a technique that enables us to look inside of the opaque granular matter in a 3D bed. And secondly, we want to use CFD-DEM simulations that give us access to more sophisticated particle quantities like single particle trajectories and mixing, but can also be used to show the gas phase flow, which is not accessible via MRI. So both techniques Both techniques have a symbiosis where the MRI experiments validate the CFD-DEM simulations, and the simulations give additional physical insight into the problem. Why do we want to use MRI? MRI has been used for several decades now in clinical applications. For example, to create high-resolution structural images of, for example, brains, as you can see on the left. And it also enables to encode properties like flow quantities, like the one you can see in the cardiac flow imaging on the right. So it helps us to get information of systems non-invasively, and this is a quantity we really want to apply for granular media. It has been shown that this can be also done for granular media, for example, with performing real-time particle concentration imaging, as you see in the image series on the left. And it is also possible to encode particle velocity with the means of MRI on granular media. So both of the quantities we really want to investigate on our problem here. All of the methods we use for MRI are non-invasive and can be used in full 3D systems. In order to do so, we need to take several steps to perform real-time measurements on a lab-scale granular system. A member of our group, Alexander Penn, performed this in recent research. So at first, he tailored a multi-channel radio frequency hardware, so a receiver that receives the signal out of the fluidized matter. Secondly, he developed high MRI signal particles. So these are core shell particles that have liquid inside of the particles, so that we have signal to measure those quantities in MRI. Thirdly, we also designed time-efficient MRI pulse sequences to reduce temporal resolution. And all of these three methods are used to create 2D slices of a 3D bed with a temporal resolution of about 7 milliseconds and a spatial resolution of 3 by 5 by 10 cubic millimeters. Now, the setup of this experiment is the following. We have the granular bed, which contains those core shell particles, so the agar particles, with about 1 millimeter diameter. Then the whole bed is set into fluidization state by inserting pressurized air through a distributor plate at the bottom. In order to really study single reproducible gas bubbles, we inject those bubbles by means of a central air injection orifice in the center of the bed. This injects a gas bubble that interacts with an obstacle inserted of the bed. In this case, we use a cylindrical obstacle, so a tube that is positioned horizontally into the fluidized bed at a position of 100 millimeters above ground and has a diameter of 30 millimeters. The whole bed that we investigated has a diameter of 19 centimeters and has a filling height of 20 centimeters. MRI studies are then used to perform sagittal cuts through the bed that give us information about particle concentration. You can see image series on the right of the slide. So different slides at different points of time, where black regions represent voidage, so a gas-filled region, and bright regions represent particle regions. For the CFD-DEM simulations, the setup is equivalent to the MRI setup. So we both use the same diameters, we use the same type of particles, and we use the same setup. Here we perform simulations with the CFD-DEM coupling software that treats the particles as Lagrangian particles with a Hertzian contact model. And the gas phase is unresolved using a CFD grid that is, has a bit larger grid spacing than the particle diameters. Coming to the results of our investigations, we see the evolution of a gas bubble around an obstacle on the left of this plot. A major bubble gets injected into the fluidized bed and then hits the obstacle, wraps around it, and splits into two minor bubbles. Those two minor bubbles do not necessarily need to be equivalent in size, so they can split into a smaller minor bubble and in a larger minor bubble. If we take the images we have produced on the left and perform digital image analysis on those images, we can track the cross-sectional bubble area throughout the evolution of the bubble in the fluidized bed. We see, for example, on the moving projection on the right, that the area of the major bubble increases during the injection, reaches an apex. When it hits the obstacle, it reduces its size, performs a split, and then afterwards, the two minor bubbles detach from the obstacle and go further. We also see that the smaller bubble that is produced during the split is more likely to decay in area than the larger bubble. So it collapses first. This performs all through the observational time. When we perform averages of those experiments, we see that we can reproduce all of those bubbles pretty good. So we have a unique characteristics looking on the image on the left. So the bubble rises, the major bubble reaches an apex, splits into two bubbles, where the sum of the bubble area is constant before and after the split. After the bubbles detach, they reach a constant plateau and then afterwards decay as they rise through the bed because they leak air that goes into the emulsion phase of the bed. The same feature can be reproduced by simulations on the right. So we can actually reproduce the same quantitative and qualitative characteristics with the apex for the major bubble at about 3,500 square millimeters. The split of the bubbles into two minor bubbles at about 120 milliseconds, and then afterwards the decay of area of the minor bubbles. So there's a very good agreement between simulations and experiments. The only thing is that the minor bubbles decay in size faster in the simulations as in the experiments. This is mainly because the simulations overestimate the permeability of the bed. However, all of the major characteristics can be found in the simulations as well. This can be used in order to validate the simulations and enables us to get a better insight into the granular bed. So for example, it is possible to see by means of simulations how the gas really flows into the bubble and exits the bubble. In the simulation on the left, you can see how the gas is entering the bubble, represented by the red arrows pointing into the bubble, or escaping the bubble at the crown of the bubbles, represented by the blue arrows on top of it. So those simulations can really estimate quantities that are not accessible or not easily accessible by means, for example, with MRI, but accessible by means of simulations. We can also see here that the gas bubbles are only maintained because of a constant inflow of gas inside of the bubble. This also helps us to explain why smaller bubbles collapse faster than larger bubbles. This is because larger bubbles represent less resistance to flow as the smaller bubbles. So flow will preferentially flow through the larger bubbles and less through the smaller bubbles. So that means more flow in the larger bubbles helps them maintain, whereas less flow in the smaller bubbles makes them decay first. We are not finished with our measurements, so we want to extend MRI measurements in order to perform a parameter analysis. We know that the background fluidization really influences the amount of gas going into the bubble and therefore also maintains the bubble. So we want to study that influence. And that also goes along with the particle diameter because that influences permeability. We want to study different obstacle sizes and shapes on that splitting and also the injection of multiple bubbles. Then further on, we want to use high sophisticated MRI techniques such as particle velocity encoding to see the particle velocities in the solid phase, and around the obstacle to estimate how mixing qualities are affected by the obstacle. This also can be used for further validations. So there are a lot of things to do and to investigate into the very interesting field of fluidized beds. At this point, I'm at the end of my presentation, and I really like to thank you for your attention. If you have any further questions, please do not hesitate to contact me. You can find the contact details on the iPosters, where you also accessed this talk. Thank you very much, and further enjoy AKI Conference 2020.